Hi, everyone. Thank you for attending this talk. My name is Eyal. I'm a data scientist at Babylon Health. Just to get it out of the way, I'm not representing my company, but rather myself. For those of you who were in Hannah's talk, that's great. You got a lot of information that I actually won't go over. But yeah, I think I'll start at this stage. So one of the things that I enjoy most as a data scientist, and I'm sure a lot of you, is modeling for challenging and interesting problems. But what I find even more thrilling is being able to get data such that to test your models, to see how well you've done. And one of my first tastes of getting feedback from real life impact was in 2016. The details don't matter, but just briefly, I was working and doing consulting for a mid-sized restaurant chain, doing some marketing for them, and I was doing a project which I call snail mail A/B testing. And again, the details don't really matter, except for the fact that we were sending them coupons via mail, and so it took months to get the data back. And so I summarized the project both as a success and as a failure. The reason I consider it successful is because my machine learning models really managed to identify people that were more likely to go into the restaurant and make purchases, and I managed to beat their standard marketing firm. But it was a failure not only because they didn't continue the contract with my company, but me as a statistician, I actually failed in the sense that I peeked into the data before it was ready under the pressure of the clients. And that's known as the peaking. And so what I failed to know at the time, and is the topic of today, is what's the stopping criteria? How do you know when you've collected enough data in order to have statistically robust results? And so this is a key feature in hypothesis testing, which is a very broad field, so there's no way that I'm going to cover all of it, but my objective is to give you a flavor so you can better understand for yourself. The reason I feel this is important is because this is the first thing that an analyst is asked for when starting a project. How much data do you need? And the common practice is to do some sort of power analysis in which one goes into a website calculator, puts in the parameters, and then kind of wings it later on. And so I feel it's kind of like a dark art, and I looked into it a bit more, and here I'm going to present a few opinions that I've collected on the time. And basically, I'm echoing a lot of ideas in the excellent blog post and book by John Krusk. Just a bit about myself. I've been doing predictive modeling and analysis for over 15 years in various domains. I started off in astronomy, later on in consulting, and most recently in biotech and in health tech. And if I do my job correctly, my objective is for you to have a better understanding about experimentation. If it's first of all by better understanding how to analyze sample data, and as a consequence, you'll be able to be better at budgeting for your next experiment. I have two main take-home messages, is that you should, as an experimentalist, you should be moving on from Frequentist to Bayesian methods, and with a focus on the theme of this talk, which is that precision should be your main objective. That should be your goal. And the second message, of course, it's kind of trivial, but it's worth noting, precision is expensive. So that's it in terms of motivation. I don't assume any knowledge of hypothesis testing, and so I'll give a very brief introduction to that. To those who do have experience, I will highlight a lot of things that I'm sure that you'll find interesting. First of all, I'll pose the problem of the standard practice of the stop criterion, which is likely to lead to biases. And so I'll talk about that as a problem, and then I'll talk about the solution suggested by John Krusk, which is precision is the goal. So we'll get into that. And then I'll summarize by talking about real-life considerations. I don't think there's going to be much time, but I do have a sample calculator, my own online, so maybe in the question time, if you're interested, it's a work in progress that I'm interested in developing further. I will start with an apology. I prepared a very long talk, and I don't have all that time. So the slides are available online. Here you have the link, and feel free to speak with me later. The main reason is that not only was I learning the topic more in depth, but I've been learning parenthood. We have our first newborn. We're not putting her gorgeous face on social media. But if you're interested, I will be passing on my phone so you can actually take a look for yourself. No, I'm kidding. Of course I won't do that. But yeah, feel free to pick me up after the talk about anything I talk about today or about parenthood. Cool, so we'll start with what hypothesis testing is. Basically, it's when you collect data in order to answer a question. Most of the time we think about A/B testing, but generally speaking, it's when we want to rule out some sort of parameter value, or more interestingly, when we want to confirm a parameter value. I talked about redeeming coupons for a restaurant in my marketing example, but otherwise you can think of cure rates of drugs, polling data, and the emphasis of this talk will be on a very simple case, is how fair is a coin that I'm tossing. The reason being it's because it's very simple and well-defined mathematically, and also it's a very useful analogy for all the other examples that I mentioned. Where right here I'm focusing on rate statistics, meaning anything between 0 to 100%, but you can use this as an analogy for anything continuous. So you can imagine, for example, a drug, how well it changes the blood level pressure. And what is the main challenge of hypothesis testing? Well, basically, you cannot apply your hypothesis to the whole population, hence you have to use a sample. And a sample, you should use it as an indication of the result that you can expect from a population, but obviously, you cannot consider it as equal. And for that reason, and the reason for that is because you might land on an extreme case, as we'll see throughout, and that's why we want to use statistics to better understand, to relate between our observation to what we think the underlying truth actually is. And that brings us to the stop criterion. Of course, we want to know how much data do we actually need, how much of the population do we have to sample. And so, of course, there's always going to be constraints, and when we work with stakeholders, they're always going to want to do it as cost effectively as possible. And of course, there might be ethical issues. For example, clinicians might be dealing with a drug that has deleterious effects, and so you would want to stop that as soon as possible. And there are various mechanisms of doing statistical significance. This is by far the most popular, a frequentist approach called null hypothesis sigma test. I have to not think the British NHS medical services when I say the acronym. And the reason that it's highly used is because it's fairly easy to calculate and familiarity. It's within all the textbooks. It was created way before the invention of the computer, and that actually brings it to its downfall, is that it's not really understood by non-experts because it's really not intuitive. And the main thing that key point that I'll talk about, I'll emphasize today, is the fact that you cannot use it to accept a hypothesis as opposed to Bayesian methods that we'll look into. So you heard various talks today about Bayesian and Bayesian talks. If you're still not comfortable with the difference between Bayesian and Frequentist, I like to use this as my go-to frame of thought. So it's just how we approach probability. So for example, frequentists rely on something called the likelihood. What that means is that you assume an underlying hypothesis, and then you ask, what's the probability of me collecting the data? Let's start with our first example, the coin toss. You toss a coin 10 times, 7 of the times it's heads, and so you say, assuming a fair coin, meaning a 50-50 split between heads and tails, then what's the probability of getting 7 out of 10? That's how frequentist thinks. Bayesians think in terms of posteriors. They use likelihoods, but the bottom line is a posterior, in which the anchor is the data. Given the data, what's the probability of my hypothesis? Given we have got 7 heads out of 10 tosses, what's the probability of our coin being fair at a rate of 50%? Or unfair, let's say 65%. So when should you use frequentist versus Bayesian? As a general rule of thumb, my opinion is always use Bayesian unless it's really too expensive for your use case. In that case, hopefully you have large enough data in which the frequentist and Bayesian should result in a similar result. But Bayesian, the main advantage of it is that it's much more descriptive than frequentist, because frequentist gives you a point measurement, where Bayesian gives you a full distribution, and so in that sense it's much more interpretable. But then again, it is more expensive, so you do have to do that cost-benefit calculation. All right, so all that was introduction. Now we'll get into the stop criterion. So again, I mentioned coin statistics. The reason I'm going to use that is that it's very simple, well defined mathematically. And we'll see just by tossing a hypothetical coin about the problem with peaking that I mentioned before. And I'll point why the NHST method is problematic. And so, well, what's the stop criterion? The stop criterion is a subjective decision that someone has to make. Either it's an analyst or it's the developer who has to write the equation within some sort of algorithm. And of course, there's, the pressure from your stakeholders to do it as cost effective, so to stop as soon as possible. And here we'll see why normally that's not a good idea. And later on, we'll see what I suggest that we should be doing. So just before we get into results, let's look at the NHST, what it is. The stop criterion is when we have a metric called p-value, which I'll soon define, which is when it's smaller by some false negative rate parameter called alpha. So here's the definition of the p-value. So it's the likelihood that, our observation, that the null value might be larger than the observation. So it's easier to understand it within a graph. So here we have our point metrics, we have the null value, and let's say we have our observation. And so what we draw is some sort of likelihood function. It doesn't matter what it really is, if it's a normal or t-distribution, that detail doesn't matter, some sort of distribution. And the p-value is just this. It's the probability that our null value is going to be larger, the probability of our data is going to be larger than our observed value. This is what's called the one-sided test. More generically, what people do is just before that, if p-value is larger than the null hypothesis, than the alpha, then we reject the null hypothesis. If it is larger, then we're inconclusive. What do we do in terms of inconclusive? Sometimes we collect more data, sometimes we come up with something else. Again, people wing it normally. That was one-sided. Two-sided is when actually, so here, one side is when you want, you're testing for the alternative to be better, but in most cases it's actually two-sided in which you don't actually care which is better. So in the case, my marketing firm versus the other marketing firm, from the point of view of the customer, they don't care. Like, who's ever better, that's all they care about. Okay, so with that definition, here we can go through some examples. So what I'm doing here is I'm testing the null hypothesis for a fair coin, where I'm starting out actually with a fair coin. So just to explain what these two graphs are, here I'm actually looking at the cumulative sum average just by tossing 1,500 times. So each time I'm stopping and I'm calculating what I think the coin value is. Here I highlighted, it's very hard to see, sorry about that. Here is the actual ground truth at 50%, and I purposely chose an extreme example in which you can see it's highly negative. And so here it's highly negative. Eventually it will asymptote towards 50%, but here you can see the p-value at each iteration. I take the p-value, and here you can see at the commonly used 5%, it will actually stop. And so if that's our stop criterion, then the observer will ignore all this information later on, and in their opinion, they have a very biased coin at like 45%. And that's their opinion. Okay, that was a very extreme example, so with anecdotes you can't get to any real conclusions. In order to do that, you want to do this like thousands of times, and that's what I do in this graph. So just to explain what this is, and apologize, I moved over to log scale over here. So what I'm doing is, just to explain, like here we stopped at, let's say, 340. And so how abnormal is that? Well, let's look at this over here. Here I'm doing iterations, and here I'm doing a cumulative proportion of decisions, where I have two options, either reject or inconclusive. So here, let's say 340 is about here. And so I can see about just about 30 or 40% of the time, when we stopped the toss at 340 or before, we rejected the null hypothesis, even though we have the benefit of knowing that that's our ground truth. So we know we're doing it incorrectly. And so John Krusk's claim is that if you wait long enough, meaning you toss a coin enough times, you're always going to get a false alarm. At some stage, you're going to stop because the p-value is going to go below your threshold. In our example, 5%. Okay, so that was a fair coin. Let's look at an unfair coin. And an unfair coin, well, you want to reject the null hypothesis. So here I'm using an unfair coin of 65%. And here you can see after 200 tosses, you get the correct result. 100% of the time, you're going to reject the null hypothesis, which is a good thing. But now I'll show the bad, is that you're still going to be biased. In what sense? Well, this histogram shows what is the sample success rate at the time of the decision. And so just to explain what this is the ground truth. This is 65%. And here you can see that the mean of all of those rates is at 72%. The reason being is that you have a non-negligible amount of samples that happen to be 80% or more. So you are getting the right thing. You are rejecting the null hypothesis, but then you want to see, well, how much is the rate? And you're actually getting the wrong rate. So you're overestimating what you're really doing. Okay, and so that's a main flaw. So how does this even make sense, right? Because you think, well, each coin toss is independent from the previous one. Well, it makes sense because what's not independent is when you're stopping, right? You always stopped like north or above, above, let's say, 60% over here. Actually, here's one on the other side. But mostly, you're not filling in this region over here because you're biased towards stopping when you're higher. In our case, because we're using a highly biased one at 65. And so that's why we get a bias. So before we got a confirmation bias, right? We were rejecting a fair coin. And now when we're using an unfair coin, well, we're not getting the correct result. It's getting too high. Okay, so one way that you can actually reduce this within HST is actually lowering alpha. If you use 1% or 0.1%, of course, you'll be able to reduce these biases, but it's at the expense of collecting more data, right? That's point number 2, precision is expensive. Okay, so Frequentist, I presented the problem. Can Bayesian methods magically improve for this? Because everybody thinks, oh, Bayesian solves for everything. And so that will be our next talk. There are various Bayesian methods. This is a fairly new field, that's been propagating. And so here I'll just show a very popular one, HDI with rope. And in order to do so, I'll introduce 2 topics. One is the confidence interval that Bayesians use called HDI, and something that's called a good enough built in hypothesis testing. So what an HDI basically is, it's you take your posterior, and then what you want to define is where 95% of the mass is. Basically, you scan from top to bottom, and you find where 95% of the mass is. And so here I'm just highlighting in this cartoon. Normally, people use like 95%. The previous talk was 94. There's online discussions. Maybe we should use 89 just to show how arbitrary the number is. But we'll just stick with 95 because people are familiar with that number. The next topic is rope. So here I'm just taking a direct quote from John Krusk's book. Basically is you just want to define, based on your domain, what region is kind of equivalent to your null value. Like in my simple task, I'm just doing anything between 45% to 55%, as far as I'm concerned, is equal to my 50%. Of course, if you work in a mint, then that will be unacceptable. You want it like 0.1% or lower. But just for the purpose of this example, we're going to take a wide range of like 10%. And so the stop criterion just says, if your HDI is completely within the rope or completely without, then you'll stop collecting and then you'll assess. Where if it's completely without, outside, then you'll reject. If it's completely within, then you'll accept. That was 2 examples. Here I'll go through actually all of them. So these are 2 rejecting examples, to the right and to the left. Then you have 1 accepting scenario. And then you have actually 3 scenarios in which you're inconclusive because you're straddling either the left or the right, or you're actually the HDI is broader than the rope. And then you have to decide, am I collecting more data? Do I have a budget for it? Or I'm just getting back to my stakeholder and just saying, yeah, we don't have statistical significance. What do we do? What I'm doing right over here is I'm using the same exact extreme example from before. Remember, we rejected it after 340 tosses, which was right about over here. Here you can see actually we're accepting the null hypothesis at about 900. Okay, that's this figure over here. And here I'm just showing you how the HDI actually gets shorter and shorter as you, smaller and smaller as you collect more data. I'm already alluding to the precision aspect that we'll get to later. So, of course, this is anecdotal. Now we want to see on many simulations. And so if before you saw that we always rejected, with the Bayesian, that corrects for it. Here you can see we're accepting the null hypothesis, and that's a big win for Bayes. So that's first one of the first arguments why you want to use Bayes, which you can start accepting null hypothesis. But there is a problem with this specific Bayes method, in which you can see that you're still rejecting the null hypothesis, even though that's our ground truth. You're still rejecting it 20% of the time. Right, so that's problematic. And let's look at the unfair coin. Well, here we're also here we're doing what we want. We're rejecting the null hypothesis. So nothing too interesting over here, similar to before, but also similar to before, we have the same problem in which we're biased. You see, we want 65%. We're at about 72%, and look how many times it accepted 85% or more, even though the ground truth is 65%. So Bayesian, HDI plus rope doesn't magically solve for the problem, but it is beneficial over NHST for three main reasons. First, you can accept the null hypothesis. Second, you get a descriptive distribution of your posterior. And in the previous talk, you heard all about adding prior beliefs. That's beyond the scope of my talk, but yeah, that's another advantage. So precision is the goal. That's the idea that I'm echoing from John Krusk's learnings, in which basically it's the same idea as HDI plus rope, but actually the stop criterion is based on the width of the HDI. So what do I mean by that is you define your precision goal in advance. How much should that be? Well, some fraction of the rope. So let's say, so it's commonly used, 80% is commonly used. So let's take that as an example. And so the stop criterion is just when the HDI is smaller than the precision goal, then you stop and you assess, and the assessment is the same as before. So just for example, regardless of where it is compared to the null hypothesis, I purposely didn't draw the null hypothesis, regardless of where it is, if it's broader than the precision goal, then you continue collecting. If it's narrower, then you stop and assess. So here, for example, here it's going to be rejected, and here it's the same exact width, but it happens to be within the rope, and so you accept. And of course, if you're straddling, then you're going to be inconclusive. Okay, so it sounds promising. Let's see what the results actually are. So I forgot the title over here, but it's the same cumulative probability of decision making at the stop criterion. And so here you can see a few interesting things. First of all, the good thing is that it solves the problem for not I should have mentioned, so here I'm using the fair coin again. It solved the problem that we're not accepting the null hypothesis anymore. We're rejecting it, okay? But there is something problematic that you're probably seeing, is that we're accepting the null hypothesis only 40% of the time, and 60% of the time, we're actually inconclusive. And so that's a massive issue with this, and so I'll address that very soon. Here I'm looking at an unfair coin, and this is kind of what you expect. You're rejecting the null hypothesis. It's a bit slower than before, as you expect, and it's more like a heavy sidestep function. But the beautiful thing is this graph over here is that here you have the true rate. The samples mean agrees with the true rate. So even though you're inconclusive when the ground truth is a fair coin, you know if it's an unfair coin, you know that, well, in both cases, you know that you're getting an accurate result. Even though you're inconclusive, you are accurate about when you are accepting, you know you are accurate. Yeah, so that's a great advantage of precision is the goal. And yeah, but of course the main challenge is inconclusive. So when I was trying to apply this in my line of work, well, I I also had to kind of like wing it, like get around, like how do I deal with inconclusive? And so one anecdote I had that while the picture I was showing is that my baby daughter was lying on me and I was creating these slides. I was also coding things up. And so I did make a mistake, and had a very fortunate mistake in which I found that actually I think we can do better than precision is the goal. And that's what I want to address right now, is something I call conservative precision is the goal. And so it's the same thing as precision is the goal, but we can improve this problem with inconclusiveness. And basically, what I coded by mistake was this algorithm. I basically combined both together. I said that, and it's just a matter of like 1 or 2 lines of code. And so I'm saying you need both the HDI to be smaller than the precision, so that's precision the goal. And then I'm using the HDI plus rope. The HDI is completely within the rope or completely without, right? So it's an easy mistake to make. And so here I'm showing that if you're straddling, then you continue to collect, but if you're completely within or without, then you can stop. And so the beautiful thing is the plot on the right. In order to appreciate that, let's look at what we saw before. So here I'm focusing on a fair coin. And so the problem with HDI plus rope, remember I talked about the fact that we're rejecting 20% of the time. And then we said, well, in precision the goal improves that by it completely rejects it doesn't reject the null hypothesis, but the problem was that it's inconclusive. And what I call the conservative precision is the goal. Actually, it has a benefit of both worlds, in which eventually it will always accept and it won't be inconclusive. So you can continue collecting data. So I'm quite psyched about that. I'll probably drop a note to John Krusk and see if maybe somebody else came up with it, but I was glad that I caught onto it by mistake. So that was a fair coin. Here, with an unfair coin, I get the same result as precision is a goal, which is good. I'm not compromising on accuracy. So that is, that's precision is the goal, but of course we have to talk about real life, how do we apply this in the real world? And the main reason is that there's always the analyst dilemma, in which on the one hand you want to be true to the scientific method, on the other hand you want to be attentive to stakeholders' need to be as cost effective as possible. And so the way to get around this is to be ensure that you have a clear objective. If there's time later, then I'll show you a demo on Streamlit that I've done. But I like this quote by John Krusk, in which he talks about the fact that the samples you want to be clear when deciding your sample size. You want to be clear on your objective and speak with stakeholders. I know it's kind of like a fuzzy territory because they come with me with different questions, and in practice it means different sample sizes for different questions, and that's what I want to get through right now. What do I mean by that? And so they pose different questions in which, as an analyst, I translate into different numbers of parameters, because the more parameters you have to deal with, that's going to be more expensive in order of sample size to get a significant result. And that's what I'm illustrating these 3 plots over here. Okay, so I'll just go one by one through them just so you understand what it means. So the first question is, I'm asked, well, how well does the model perform? Like, give me a number. And so if I think, of course it depends on your domain, but going back to the coin toss, which is a useful analogy, well, all I need is 2 parameters. I need to know how many times I've tossed and what rate have I been successful, and then I can tell them, like give them some sort of distribution of how well the model performs. Okay, so that's one type of sample size. But if they ask me something different, let's say, look, we have to pass a certain threshold. We have to pass like 70%. What's the probability that we're passing 70%? Well, that's another parameter that we have to improve upon, right? And so that might impact the sample size. So you want to take that into account if you do precision is the goal method or anything else, okay? Another thing, of course, the most popular question is variant A better than variant B? Right, so now you have like 2 different coins, right? Is one coin biased, is the other unbiased, or whatever combination? And so that's 4 parameters, right? That's how much are you tossing one, tossing the other, and how successful are you in each? And so the more parameters, that will impact your sample size. So you want to define this in advance. And so my point being is that you want to be as clear as possible in order to determine your sample size. And the reason being is when you're planning your budget, all your data is hypothetical. And so you have a lot of parameters to play with. And so that's one thing that in my calculator that I'm looking into is like how to change the different variables, where of course the more easy thing is once the data is a stated fact, and then how do you interpret it and avoid misinterpretation, as I talked about before. And so we're at 30 minutes. I'm going to spend the next 5 minutes summarizing all that we said. If there's time later, we'll go into this calculator that I created. But in any case, it's online. Feel free to go into it. Yeah, so thanks to Streamlit that hosted. It's really brilliant. I actually couldn't get it to work on my laptop at the last minute, so I'm very thankful that they have it up and running. Okay, so I'll just skip these. These are just my working examples on the calculator. One thing my calculator does not include at the moment is what people are most interested in is A/B testing. So I will point you to very useful resources online. John Krusk has an excellent paper called Best, promoting the idea of Bayesian statistics. There's an alternative approach. Instead of precision is the goal, it's something called expected loss criterion by Chris Struccier. So you want to look him up when you're comparing methods. Evan Miller has excellent material and calculators himself. And I like this blog post that actually summarizes all three. So yeah, I very much encourage looking that up. I do not, oh, I clicked his site by accident. Sorry, do not know why. Okay, yeah, so if I've done a good job today, hopefully you have a better understanding of experimentation. And what I'm encouraging you to do is improve the way that you interpret data. And by that, you'll be able to improve how you budget for collection of data. Where my main take-home messages are, you should start using Bayesian methodology as opposed to the Frequentist, and of course, precision is expensive. To those who managed to dig a bit deeper with me, I'll just summarize the key topics. I talked about the problem with the extreme methods for the STRUP criterion, the Frequentist and NHST, and the HDI plus ROPE. I showed that they're likely to give you biased results if it's confirmation biased, or just the sample rate will be biased. And I encourage precision as the goal, as the methodology. When it comes to Bayesian, in general, you want to use that because it's more interpretable. And in terms of hypothesis testing, is because you're more likely to, because you'll be able to accept the null hypothesis, something you cannot do with Frequentist. Hypothesis testing, there's many topics in this field, so I'm just highlighting a whole myriad in which I haven't had time to address. If it's power calculations, usage of priors, multiple hypothesis testing is a huge issue for Frequentists. It's not an issue for Bayesians. I used analytical solutions, very simple coin toss before you heard it talk about numerical solutions in which you want to use PyMC and a whole field of stratification of cohorts. Of course, that makes life much more complicated. I kept things very simple. Just to summarize, yeah, hypothesis testing, I find it requires defining a clear objective in planning so you can have a realistic budget and good interpretation of your data. We talked about the fact that NHST and HDI plus ROPE yield biasing results, and precision is the goal. Gives accurate result. It does have the issue of inconclusiveness when you when the null hypothesis happens to be true, and I suggested an alternative as the conservative precision is the goal. As a possible improvement. Just before I give time for questions, I want to mention, if you enjoy this talk, just self-promotion. I have 2 other talks that I've delivered in previous conferences. One is just a gentle introduction to causal inference, and the other is a tutorial in which you learn about a topic that's called, it's a mouthful, it's multi-objective optimization. Effectively what it is, how do you deal with 2 or more objective parameters that might contradict each other or be in conflict. And so that's a topic called Pareto fronts, which I'm pretty enthusiastic about, and I created Jupyter notebooks with demos. So yeah, so with that, I'll take questions from here.
Thank you very much. And I have the first question. Yeah, interesting, the conservative PITG. Thanks for the talk, by the way. First question is it robust also over like multiple different types of data generating, data generating processes? Because in this case, it performed really well. But have you tested it also in with other data generating processes? And then the second question is, if you would add to it that it doesn't like peak at every iteration, but maybe only every 100 iterations, would that make it even more robust or not?
Okay, so just to reiterate the question, thank you for the questions. So the first question is, he pointed out the fact that I used it only on Bernoulli statistics, just a coin flip, which is rates, but of course you can use like a continuous variables, let's say a Gaussian distribution or something like that, or something more complicated. The answer is no. I'm assuming that these are useful analogies, but I haven't looked into that. I didn't understand your second question.
Well, yeah, I also have used the analogy that it's kind of like peaking is kind of like risk of ruin, right? If you like peak too often, the chance of seeing a certain outcome that's wrong is increases. So, but you kind of want to keep collecting data.
Yeah.
So couldn't you like keep collecting data, but only every 100th iteration you're allowed to apply that stopping condition? You know, if
I see. Excellent question. So the question is, okay, so let's say you get a result. I'm assuming, let's say it's inconclusive. How do we how do we continue when we're inconclusive? And so my opinion is, when I applied it, I like precision as the goal, because you define your precision, and then you just well, if you're inconclusive about the precision, well, just define your next precision, how much you want to go to. And that's kind of something that I played with my stakeholders, in which we got to an inconclusive result, and then we just continue collecting. We define in advance how much more data we need. Well, the idea was the following, is when we decide the precision is the goal, I defined like how much sample I want to collect, but the sample rate we got was different from the base one. And so I said, okay, that's no problem. Considering we got a different base, we got a different result from our base, we still have the precision. If we collect more, let's wait till we get to that precision. Because I was bound by stakeholders who have a budget. They don't care about precision. They care about how many samples should we collect. That was the main problem with stakeholders. They don't care about precision. As an analyst, I care about precision. They care about n number. So what happened is I gave them an n number. The truth happened to be different from the base that I assumed, and said, that's no problem. I still have my precision goal. I gave them, here's the next number that we want to go to. So that kind of answers your question. We started, and so that enables me to not peak. Well, it enables me actually to peak, because I'm fine with peaking, because my goal is the precision. Yeah. Sorry if that was incoherent. I should have prepared probably better on that. Yeah.
Thank you for the presentation. So, do you think that this method could be applied with frequentist confidence interval? Because I struggled before to justify the use of HDI in high data regime when confidence interval and HDI tend to overlap quite massively from a practical point of view. And if you have a friendly stakeholder that listens to you, it's fine. But if you have someone that is strongly convinced that, I don't know, frequentist methods are the way to go, do you think we could apply these methodologies in a frequentist framework?
Well, I'll show you one thing that I'll address the thing. So your question is, could we use confidence interval when working with stakeholders, especially with stakeholders when they're, because stakeholders, they understand frequentist and not Bayesian? Is that?
Or apply the precision method that you specified today using confidence interval, obviously correcting for alpha.
I see. Interesting. Okay, thank you for that question. I haven't looked into that, but I do want to flag, I believe like showing like stakeholders like visuals help them like get them from Frequentist to Bayesian. So I think I'll address like that. I'm just looking up a hidden slide that I had. Yeah, here. Can you see this? Yeah, you can see this. Okay, so here I'm showing basically my point before was that Frequentist and Bayesian yield the same result if you collect enough data. That's what I'm showing here on the left. So here, 3,000. So in orange, I'm showing the credible interval for the posterior of just the beta distribution. And you can see here I'm showing like the Frequentist, something called the Agreski-Kohl, in which here's their 95%. So in that sense, they agree, you collect enough data, that's great, you can show that. But what you want to show your stakeholder is what happens if you're running a budget, let's say 30, right? Your size is 30. Well, here you can see they're a mismatch, right? And Agreski-Kohl, actually, if you look at the formula, you can get more than a rate of 100%. And so it's really awkward conversation. So what I do, I just sit with the stakeholder, I just show them like, this is why we want to shift to Bayesian thinking. It requires a bit more thought, but it's well worth it. It's much more descriptive, and so it's more interpretable, where Frequentist is not. Yeah, so that's one answer. Plus the other is that NHST, you cannot accept the null hypothesis. You can only rule it out. Yeah.
Fantastic, and we'll just have one more question.
Thank you so much for the presentation. I have a question about rope, specifically.
About?
Rope.
Rope, yes.
So in many cases, I understand that you can specify the region of practical equivalence, and maybe it's based on your business logic that something is, generally applicable or equivalent. In some cases, you might not know specifically what that equivalence might be. So let's say you hope that a feature brings you, on average, 1,000 euros per day or per given time interval. If it's between 990 and 1,010, maybe that's okay. But maybe 950 and 1,050 is already okay. It's a bit more uncertainty. And maybe different ropes might give you different answers in the first place. And I'm just trying to understand whether you can use rope or instantiate it as a random variable with some also priors, and then you can see how your results change based on these priors on your rope.
Yeah, no, that's an excellent question. So just to summarize the question, how do you know if your rope is correct, or that should be another parameter that you'd be playing around with? So I'll give you my generic answer. Anything that has to do with subjectivity and statistics is that yeah, a lot of people believe that statistics is like an objective field, but no, like there's always going to be subjectivity, some finger in the wind, and our job is to do something that is reasonable, and we have to convince first ourselves and then our stakeholders. You're asking specifically about rope. Yeah, that's something that I play around with just to see what's reasonable. My stakeholder has a budget, and so I cannot bring the rope to be too small, and so I need let's say in my case, I couldn't go more than 1,000 samples, and so my rope, I have to determine it such that I'm not going to pass 1,000 sample regardless of where the result is going to be. If it's around 9, well, you have a prior notion of what the base, right? That's part of your calculation of where your base is going to be. Is it around 90% or is it around 70%? That will have a massive impact on your sample size. So yeah, I appreciate that I haven't fully answered the question, but I guess the answer is you just have to play around with it. Would it be equivalent to peaking? I see. No, I see your question. So your question is, should I determine rope in advance or after?
Well, that's the follow-up question, yeah.
Okay. Well, no, you should do it in advance. Yeah. You should do it in advance. I don't have any experience like doing it after, so I'm not sure how to answer that question. But just from reading from John Christ's material, yeah, that's something that you wanted to determine the precision and the rope in advance. So hopefully I answered your follow-up question. I don't know about your first one.